Okay, so once again, you should have seen that 3 blue, 1 red video, sort of like roughly what these are. And this kind of picture represents a formula that maps the inputs to the outputs. So let's go over what the formula is before I reveal what you guys said. Let's write down the formula. Okay, I need a new piece of paper. And so this picture that looks like this, so these are the inputs. Let's give them a name. Let's call them x1, x2, x3. Those are the inputs. And so this is like some example where you have x number of dimensions, right? So in like the housing data set, it was like 100 or something. It's the number of different features you have for every guy. And you have an output. And in this case, the output is one-dimensional. And when you connect them up like this, that means a specific formula. And the formula that it means is every edge here represents a weight. So you got a W1, a W2, a W3, all the way up to a Wn dimensions. And I also said there's a bias. Sometimes people draw the bias in like this. They say bias, or they say bias, and then they write B. And this combines to give a formula, and the formula is you multiply along the edges here. So the formula is the output is x1 times W1 plus x2 times W2 plus dot, 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 plus all the way up to xn dimensions times Wn dimensions. And then you add on the bias, plus B. Okay. So that's what the formula means. That's what the picture translates to a formula. And these weights and biases, these are the parameters of the neural network. This is something we've done before in the course. It has a cute name, and the cute name is what? Let's find out if you knew. The name for the model is linear regression model, linear regression, simple linear regression. A perceptron is this picture, but it has one extra nonlinearity. So it's almost a perceptron. You could say it's a linear perceptron. And I think the simplest way to say what the right answer is to say it's linear regression. If you said linear regression model, of course, that's perfectly equivalent. Same regression. I think the key thing is that it's linear here, or simple. Yeah. So very good. I think most people got it. A few people did not. But that is the right answer. So this is the linear regression model displayed graphically in the neural network picture, like pictogram language. Any questions or comments about what this guy is doing? Okay, so now I'm going to show you how do you take this picture and put it in your computer. So for linear regression, you could just say, scikit-learn linear regression, like go do the thing, and it would magically do all this for you. But with neural networks, you have to be able to do it on your own. And that way you can program very complicated neural networks by like stacking together many of these layers. Nowadays things can be a little bit more automated, but this skill of sort of being able to combine various layers in different ways is a very useful skill. So that's what I'm going to show you, starting with the most basic thing. How do we put this in the computer? And that's what I have in this little example. So this example with blanks. This is the example with blanks. So we're going to build up. We're going to start with this linear regression. We're going to get more and more complicated, and we're going to get to a very impressive model that gets like 90% accuracy. And the data set I'm going to use is one I showed you earlier in the course. It's called the MNIST data set. Let me run all this. Let's start by importing everything. So let me even importing stuff is a good place to start. Let me make a copy here so it saves my things as we go. So the first thing to notice is it's using something called JAX. So JAX. So in the course previously, I've used NumPy, which is NP, which is like vectors and arrays in Python. This is using JAX.NumPy. What is JAX? Let's look it up. JAX NumPy. What is this? I guess let's just go to JAX. Hopefully this will have what I want. JAX code is the thing I want. Here it is. So JAX is a library for array-oriented numerical computation, like NumPy, but it has one extra thing that NumPy doesn't have, with automatic differentiation. So that lets you do gradient descent very quickly. You'll see when we get there what this is. So this is like the secret sauce that's built on top of it, and it has high-performance machine learning built into it. So it's faster than NumPy, and it has this automatic differentiation. This is like the secret sauce that makes machine learning work. So that's what we're importing to start. We're importing this. Let me do it in here so that it's saved. Okay, great. And we're going to do this data set called the MNIST data set. So this code I copied and pasted from somebody else. This is getting the MNIST data set. The MNIST data set, if you remember, is a data set of images. So they're little images. They're like low resolution pictures of digits. Here's what they look like. Here is me getting some of them, and I'm downloading them. And then here is what they look like. So there's a train set and a test set, and I'm only getting 10,000 of the train set. There's even more, but 10,000 is enough for us. And here's what they look like. You can plot them as a little bit of an array. So here's what they look like. Here are 4 of the pictures. So this is a picture 0. It's a 28 by 28 pixel image. The label is 0. This is another 28 by 28 image. The label is 4. These are like pictures of something somebody wrote on a letter, and we labeled them with a human. So this is the data set we're looking at. I think we did this one earlier in the course. Any questions or comments about the data set? So the question is, can we use our neural network to do it? And the first thing we're going to try is linear regression. One thing to notice is these 28 by 28 images, you have to know what is 28 times 28. 28 times 28 equals 784. So for this problem, the dimension here is 784. So for our problem, which is the MNIST problem, n dimension equals 784, which what we got from 28 by 28, but we're ignoring the 2D structure and we're just treating it as one vector of size 784. And all of these things are the pixels. So x1 equals how bright is pixel number 1? How bright is pixel number 1? x2 is how bright is pixel number 2, etc. And we're going to input all those things, and then the output we want it to label, is it a 0 or a 1 or a 2 or whatever. And the output we want it to be, what is the label? Okay, let's see what it looks like to do linear regression. How do we make this picture appear in our code? Okay. Okay, here's the code. So the first thing we got to do is generate some random starting parameters. So the key to neural networks that makes them a little bit different than all the other things we've done in the course is there's a very general way that which we find the parameters. We always start with random parameters, and then we train them with gradient-based methods, like gradient descent. We did a little example of gradient descent earlier in the course. And you have to kind of do this all from scratch. So you have to take the parameters and see how they're evolving and update them. Whereas when you do like scikit-learn linear regression, it does the optimization for you, and it's usually like linear algebra-based or something else. So this is a more hands-on way. And really, we're very explicitly saying, give me all of these parameters, W1 to Wn dimensions, give me the bias, and I will keep track of them, and I will update them as we're learning. So that's what I'm going to do right now. And here is the code to do it. So this stuff, random layer parameters, gives you some parameters to start off with. And they start out randomly. When you do things with random numbers in JAX, you need to pass around these random keys. So I have this input called key. Key is a random key. I'm starting it out using the current time. And that way, every time I run it, it's going to be different. But JAX has this interesting property that there are no true randomness. Everything has to be a deterministic function of everything else. And that's why we pass around these keys. So technically, it's not random. It just depends on what time it is. But these random keys, they are used to make the random numbers. And that's what I did. OK, so I'm not going to go too into this, how this thing works. But it makes some random numbers and initializes the thing. OK, here is what I wrote. This is the first important line. Layer sizes are 784, 1. This is exactly the picture that we started with. So by saying the layer sizes is 784, 1, I have told the computer, OK, make a vector over here. This is the first layer, or the 0th layer in Python, the 0th layer. And then I said its size, 784. And the first layer, right, which is actually the, starting at 0, it goes 0, then 1, is size 1. Let me move this bias guy so it's obviously more part of this layer over here, because the bias lives over here, goes in here. So the first layer is size 1, And that's actually the output. And really it's the second, but Python starts at 0. So the 0th layer is here, the first layer is here. And that's what I told it when I did these layers. So I said layer sizes is 784,1. And then I said, please make the parameters of the network, which is this function, applied to the layer sizes using the random key you had. And that made some parameters. Let's see what the parameters look like. So I'm going to ask it, please tell me what are the parameters. So it just made some parameters. Now please tell me what they are. And here's a big long list of what they are. It's a little bit hard to see what they are. It's a little bit easier sometimes to look at the code explorer. So if you go to this thing on here, this is the variable explorer. And if you go to params, it tells me what is in params. And params is a list of numbers. Why is it a list of numbers? Because we're going to have parameters for each layer of the network. So we have these layer sizes 784,1. So we actually have layers and parameters as a list with the parameters for each layer. So why don't I, instead of doing parameters, why don't I do parameters of 0 and parameters of 1? So parameters of 0 is a thing. What is parameters of 0? Let's give it a name. Let's call it a 0th. I don't think you can start with a number. 0th layer params equals params of 0. And if I run this, oh no, did it complain? Ah, okay, it doesn't like these. Let's okay, 0th layer params, and now I can look at it. It should appear in my variables, and I can ask about this. Where is 0th layer? There it is. It's a tuple. So the 0th layer parameter has 2 things in it. The first thing is a big long array, and the second thing is another array. So the 0th layer parameters have 2 things in them. Why don't I see what those are by doing 0th layer params of 0 and the first thing. Okay, let's print these out so we can see them. Okay, so 0th parameters of 0 is this big long list. Oh my goodness, it's so long. But 0th layer params of the second thing is just a number. What are these 0th layer params? They are literally these 2 things that I talked about. So the 0th layer params, it is 2 things. It's got all the weights. That's the first thing in it. And it's got this bias. So the 0th layer is size 784 plus the bias and the bias. So it's got 2 things in it. And actually, instead of asking it, please print it out, which is a little bit overwhelming, you can say, print out the dot shape of it. And that will be a little bit easier to read. Let's see if I print out dot shape. What does it say? Here it is. So in the 0th layer, the parameters of 0 tells you the 0th layer parameters. And the first thing in there is a 1 by 784 array. Those are my weights. And the second thing in there is a 1 comma. It's a single number. That's the bias. So this 1 comma 784 is a vector of all these different weights, the purple weights. And the 1 comma is that bias. So the network has been set up to create these things. And okay, now that you know what it is, it's actually not so difficult to see how I made it, right? So when I made it, how did I make it? Init network parameters says go through all the different layers, and make random layer parameters of the right sizes. And what are random layers of the right sizes? It's making weights, which are the right sizes, and that's making a bias. And this bias is the size of the layer, and the weight is connecting the sizes of the previous 2 layers. So now you know that it's 1 by 784 and a 1 comma. It's not so hard to see how it was made. And they started out all Gaussian. That's what random.normal means. Okay, so far in our computer, we have layer sizes as a list. We have the parameters, which are storing all the things. You guys with me so far? Any questions or comments? And again, if you want to follow along on your little copy, you can do that. Okay, so now we're going to make our function. We got these parameters. We want to explain to the computer what is this output function. We want to put this formula, the output equals this, into the computer. And that's what we're going to do. And we're going to make a function that does that. So we're going to create our function and our loss function. So here are the layer sizes and the parameters again. And this is the function lin_r, which inputs the parameters and the image. The image is what I called x before. So it inputs the image. X, it inputs the weights and the biases, which I call w and b. And you see I'm unpacking it, right? Parameters was a tuple where the first thing was the weights, the second thing was the bias. If I do w comma b, it'll get the w and b. And now I have w, b, and x just like the formula over here. So W, B, and X are all named exactly the same as they're named over here. I just have to put in this formula. All right, and there's a spot here that says fill in the output. The lin r output equals, and you have to tell me the formula, okay? And then if we type it in correctly, it will do this formula. And the question for you is, what do you type to make this work? If you're following along on your computer, you can try typing it in and see if it works. If you're not following along, you can tell me in this little word cloud, what should I type in? How do you implement that formula that I said before? How do you put that in the computer? Okay, and I'll let you think for a minute. Type in whatever you think I should type in, and then we'll do it. Okay. So what was that?
Where can I find this now?
Where can you find it? Yes. So if you go to the course GitHub, which is now mcnika89/data6100, and you go to neural networks, and you go to MNIST example with blanks, then it will take you there. Did you find it? Okay, great. Okay, looks like people need more time. Let me give you another minute. Feel free to talk to your neighbors and like speculate on what could be in this thing. How would you type this formula into the computer? Okay, 20 seconds left. Put in your guesses. Even if you have no idea, you can put in an IDK. If you don't, or if you really don't know, if you have a guess, put in your guess. That's more useful if you have one. Okay, time is almost over. Okay, put in something so that I know you're here, and let's see what people said. Okay, let's get a nice little word cloud of the answers. I don't know. Very good answer. So this is a great answer. Okay, most common answer is W times X plus B. This is very tempting, and this looks like what it should be, very morally speaking. If you do this, the computer will not complain. The computer will put it in and be like, yeah, sure, no problem, W times X plus B, and it's not what you want. So this is why I'm doing this question is to warn you away from W times X plus B, because W times X plus B is something, but it's not the something we want, okay? And the reason, really what's going on here, what we actually want is a kind of matrix multiplication. Really, you can think of X as a column vector and W as a row vector, and we're doing like W as a vector transpose times X, and this is like matrix multiplication or vector multiplication, matrix / vector multiplication. That's what we want. And what you have written over here, or what some people have written, and is very tempting to write, so it's not like they've made a big error, they've made a very natural error, they've written w times x plus b. And times is also multiplication. We want multiplication, times is multiplication, but it is the wrong type of multiplication. So warning, times does not do matrix vector multiplication. If you do w times with a star x, this is a different type of multiplication. It is blank multiplication. Does anyone know what type this is? Multiplication.
Scalar multiplication.
No, scalar multiplication would be if w was a number. So scalar multiplication in linear algebra class is when you take a vector and you multiply it by a scalar. In this situation, they are both vectors, so it's not scalar multiplication. This is a vector, this is a vector. Is not scalar multiplication. Great guess. What other kinds of multiplication are there?
Product.
It's not the dot product. The dot product is this kind of multiplication. So dot product is also a type of matrix vector multiplication, like a linear algebra multiplication. This star is something else that you don't see very often in linear algebra class. You see it a lot in computer class, I guess. Byte size? That might be what I've never heard that before, but it might be the same. Byte wise, is that what you said? Yeah, that might actually be exactly the same as what? What is it? Binary? It's not binary. It has nothing to do with binary. I'll give you an example of what it does. Let me show you, and then you can figure it out. So if you have 1, 2, 3, and you multiply it by 4, 5, 6, I will tell you what the output is. The output will be 4, 10, 18. It'll be 4, 10, 18. What is it doing? What is it? Yes, it's just doing the entry-wise multiplication. So it outputs a vector, and what it does is it takes 1 times 4 and gives you a 4. It takes 2 times 5 and gives you a 10. It takes 3 times 6 and gives you an 18. So this is entry-wise, is one word for it. Entry-wise multiplication. That might be the same as byte-wise, depending on what byte means. But basically what the computer is doing is saying, oh, w and x are vectors. If w and x were numbers, it would just be ordinary multiplication. If there's 2 vectors, we'll just repeat the operation for every entry in the vector. So be very careful with this. The default operations are in most of computer class are entry-wise operations, like entry-wise multiplication and so on. Whereas the default operations we want when we're doing things like linear regression are the matrix operations, and those are not the default. So you have to somehow tell the computer, hey man, I'm doing multiplication, but not that type. I'm doing this type. And so you got to put something else in. So I think this is a very important warning, worth spending enough time on, that you guys get it. W times x is tempting, but wrong. I will say there is one way you can rescue w times x. Let me see if anybody had the rescue of w times x. Let me see quickly. Here's another w times x. Here's somebody wrote it out. Of course, you can't do this one because you don't know how long it's going to be, right? So like it could. In our case, it's 784, but you need the computer to somehow do it. I guess you could do it with like a for loop or something. This person has rescued it. So this person knows exactly what's going on. If you do sum of w times x plus b, that will work. And that's because w times x is this vector. Let's see, in our situation, what is w times x? It will be w times x will be this vector, w1, x1, comma, w2, x2, comma, w3, x3, and so on. And then if you do, please do the sum of this vector. So you say, please do the sum. That will work. And then you will get w1, x1 plus w2, x2 plus w3, x3 plus dot, dot, dot. So if you did that, perfectly correct. And it's exactly taking the entry-wise operations and then summing them. That is what we want to do. So that will work. You need to write, if you write sum, it won't know what you mean. You have to do jnp.sum. And that is the sum command from the library we're using. That will work perfectly well. So very good. And let me see, did anybody else? Yeah, lots of other people fall for this times thing. So it's a very good thing to know. Okay. Okay, great. So we have one solution. Any questions or comments about this? I think this is a good thing. That's why I brought it up. It's like almost everybody, that's like the natural thing, but it's not quite right. Yeah.
The one that you told solution, so I wrote that.
Mm-hmm.
So is it dot product in the thing like sum of?
If you do this,
Yes.
Uh,
Dot product.
I mean, it's equivalent to the dot product, but it is not the same command. And actually, if you do this one, it will be slower than just doing the dot product directly. And that's because in the computer, you're doing two operations. You're saying first do this, then do this. Whereas if you say do the dot product, it's like smart enough to do it all at once. So how do you do it? Actually, one person has it written down. If you do this, JNP dot of WX, that will do the dot product. And so this is the simplest possible thing. The JNP dot will say, please do the dot product of W and X, and everything will work perfectly fine. You can also say matmul, JNP dot matmul will do a matrix multiplication, and if the sizes are correct, it will work. That will also work. There is one other shortcut. Let me tell you what it is. If you want to do a matrix vector operation, you can do an at. So you can do W at symbol X, and that will do matrix vector multiplication. If the sizes are correct, it will work. But the simplest thing in our situation, I think, is to do JNP dot. So, or JNP dot. You can do matmul, I believe is called, of WX. Or you can do, in this case, dot WX. And all of these things are slightly different in the cases where W and X are bigger shapes. Like if you do JNP dot and W is a big array, it will do like the dot product of all the different like entries of W. But in our situation, all of these are the same because W is just a vector, so it's all fine. And all of these will work. Okay, so let's put it in. And we're working on it over here. We're doing JNP dot of W and X. Am I forgetting anything?
Plus B.
Plus B, yeah, very good. So plus B. Okay. Is this gonna work? I feel like this has, let's just try it. I think we're missing one thing. Oh yeah, maybe, okay. So let me try it. So here I ran it. Yeah, okay, great. So here I ran it and I said, please tell me what is the output of the linear regression function using the parameters we have on the 0th training image. And it outputted this. Square bracket, 9.03 square bracket. So what this is telling me is that the linear regression function right now, it doesn't output a number, it actually outputs like an array of numbers. And we want it to output a number. So I just have to do one small thing. I'm just gonna add in, please give me the 0th element. So it's kind of something of shape 1, like it's one number. If I do this, now it really gives me a number, and now everything will make sense. So you could make it work the other way, but this will get a little more conceptually fair. But that's the right answer here. Okay. You guys with me so far? Any questions, comments? Yeah.
So do we need activation function in this?
Is there an activation function in linear regression? No. There is no activation function in linear regression. We're doing linear regression, and so we don't need one. You'll see that the linear regression, I'll give you a spoiler, it's not going to work very well. And we're going to improve it by adding an activation function. And we've actually done the hard work now. Once you say like we just need to add an activation function, it's like 1 second to add. So it's very easy to add an activation function once you understand this stuff. So this is the hard part. The activation function is very easy to add. Will take 1 second to add up. So that will be quick once we get there. Okay, great. Any other questions? Okay, let's see how to do the rest of it. So this is the function. Now we have to apply the function to all the training images and then do our gradient descent, like we talked about several classes ago. So that is the method we're going to use for training. And it's very tempting. If you take this linear regression function, it inputs the parameters in an image and outputs what it is. It's very tempting to start writing like this. You say for I equals 1 to 10,000, because we have 10,000 training examples. And it's tempting to write something like that. Well, what it's suggesting to me. So look, we did it one time. Now do it 10,000 times. Just do it on all the images. And okay, even though this one takes 0 seconds and is really fast, this one will take a while. Let's see, it's still going. Oh no. And so what is the moral of the story? Doing one image is quite fast. Doing 10,000 images took 7 seconds, which is quite a bit slower. And actually, if you see this kind of code and you're kind of in the world of neural networks, you will cringe and start to think this is quite terrible. And the reason is for loops are really, really slow. So when you're writing this code, sort of we're telling the computer to do things, and some of it happens in this JAX package, which is really highly optimized. Like for example, when we said JNP dot, super highly optimized, super smart, uses vector operations. You'll notice I could have done this with a for loop, right? I could have said for I equals 1 to 784, do wi times xi. That also would have been really slow, and this is way, way faster. And it's the same thing with looking at all the images. So the way we're going to look at all the images, we're not going to do this. This is too slow and bad. So we're going to try to avoid for loops when possible. And instead what we're going to do is we're going to operate in a batch dimension. So we're going to add a dimension of size 10,000 and do all the images all at once. And that is the next little section here, which is called vectorizing the thing. Okay, well, let me delete this stupid output so that it doesn't do anything. Pass, okay. So I can see the next line. Oh, I guess it still takes 7 seconds? No, okay, there we go. Okay, okay, here we are. So this is the batched linear regression, which instead of doing them one at a time, it does all of them all at the same time. And in this situation, what you could do is you could stack up your training images into, instead of having x be one image, you could have x be an array of images, and instead of using dot, you could do matrix multiplication, and it would automatically do all the columns. That would totally work. However, there's an even sneakier way to do it, which is the magic of JAX. JAX has an operation called batching or vectorizing. Did they mention that over here? Let's see. JAX functions can be automatically vectorized to efficiently map them over arrays representing batches of inputs. So one of the magical things about JAX is if you write your function to work on one example at a time, it will automatically upgrade your function to work on vectors of images. All the images will work all at once. And the command to do that, it's a little bit tricky to do this. I will just tell you the answer. The command is a vmap. Vmap. Where's my thing? So the command is vmap. So you do jax.vmap of the function we had before, so of the lin_r function. And this will essentially work. So say, take the function lin_r, that's a function, make it work on vectors. That's jax.vmap, and that will be the batched linear regression. There is one other thing you got to do, is you got to tell it, okay, which dimensions are we batching? And in this situation, the right thing that we want to tell it is, I'm looking at my cheat sheet over here. So you say in axes equals none, comma, 0. Okay, none, comma, 0. And this none is telling the computer that I'm going to put in, when I do the input, instead of inputting an image of size 784, I'm going to input 10,000 images by 784. And so the none stands for the 10,000 images. The 0 is the 784 before. So these are the indices of the axes that we're doing. The none is what we're batching over, and the 0 is the 0th thing. So this is the right thing, and now it will work. And now I can feed in all 10,000 training images all at once. Let me, to make things fair, let me move this one to another code block. So if you just run this, now I've created the batch linear regression function. Now it's going to apply the linear regression function to all 10,000 training images. And before it took 7 seconds with the for loop, I want you to guess how long it's going to take when I hit play. So I told you it's going to be a little bit faster. Let's see how much faster. So you can take a guess in your head how long you think it'll be. Let's do it. Okay, it's instant. 0, I guess it's infinitely faster. No, you could time it. It would be it's like 100 times faster, or like 500 times faster, or something like that. Somewhere between 1 and 100 times, 100 and 1,000 times faster to do it as a batch than to do it with a for loop. So you really don't want to do a for loop. Modern machine learning cannot train in time if you do for loops. You have to do everything with array operations and vectors. And you can see, actually, we can make sure that's working correctly. The first one we got 9.036. That was exactly what we got for the first example before. It's doing all the vectors, all the examples, just doing it all at once in a big vector. Okay. Questions or comments about that? Yeah.
Could you please explain the meaning of these outputs? Because the training set we have is all kind of written digits from 0 to 9.
That's right.
Yeah. So
Yes.
But some of them are larger than like 31.
Yes, that's right, because we haven't trained the network yet, right? We have random parameters, right? So far what have we done? We've made the W's and the V's completely random, and then we applied this function, do x1 times w1 plus w2 times x2 for all the images, but we haven't trained it yet, right? So if you were doing it in scikit-learn, you would have to do like model.fit and give it the training set, and then it would do some optimizing to find good weights. But we are about to do it. We're going to do it with gradient descent. So far we haven't. We've just started the network. It starts out at some very bad point. Of course, like, what was it? Yeah, 31 is a terrible guess. Actually, 9 is also a terrible guess because I think the first digit is a 0. So far, this is just random noise, but the next thing we're doing is we're gonna train it. Yeah, so great question. Other questions? Okay, how do you train it? This is where all of the things we did at the beginning of class and why we need to know how these models work under the hood. We can't just do scikit-learn.fit. We have to understand what's going on, is because I'm gonna tell it exactly what to do. I have the mean squared error loss, and I'm gonna tell it, look, this is what I'm trying to minimize. This is the loss function I'm using, and then the computer will just minimize that. If you have a slightly different thing, you have some like weird thing, like you want to do the log mean squared error loss. Some people did that on the housing data set. You can do that. So you can do all sorts. You can put any function you want in here. It just so happens that I want to do the mean squared error. And here's what this looks like. So the mean squared error loss, I get the predictions, which are all for the parameters and the images. I get all that big list of predictions, and then mean squared error equals blank. Mean squared error equals blank. Okay, I don't have mathematized for this one, but please think for a second. What would you type in to get the mean squared error? You have all the predictions. This vector called target tells you the answers that you want to get. How do you combine predictions with target to get the mean squared error? And think for 1 minute on your own. You'll see the answer in a second, but you should be able to do this. Or think of like mathematically what it would be. So I'll give you a minute to think, and then I will tell you the answer. Yeah?
In Python, there is like map function.
Yes.
So vmap does work like that.
No.
Like applying a function to.
So VMAP stands for vector map. And what it does is it inputs a vector. The VMAP function inputs a vector and applies the function to every entry of the vector. So it is kind of like a map.
Yeah.
Map is for lists, though,
Yeah.
right? So map is like you give me a list, I apply the thing. So it's a vector map, if you want. Yeah. The word map in math just means like convert, like take one thing, make it another thing. Yeah. Okay, a couple seconds left. I'm going to tell you the answer very shortly. Okay, time's up. Does anyone want to volunteer what they think I should write in for this mean squared error? And again, it's very instructive to think of like what you would write and what the common errors are. I'll give you a hint. It starts out with you do the predictions, which are some numbers, minus the target. So that's the difference between what I predicted and what I was supposed to predict is the target. Then what do you have to do? Square it. Okay, great. Square it. One way to square it is to do star star. There's also like jnp.square, which can be, or jnp.pow, comma 2. But just for simplicity, I'll square it. Is that the right answer? Okay. Yeah, you got to do a mean. Okay. So, and the very easiest way is to do jnp.mean. So before I do it, let me say what's going on. So predictions is a vector. Target is a vector. You subtract them. You have a big vector of numbers. When you square it, this again is the entry-wise squaring. So now you have this is a big vector where every single entry was squared. The mean squared error, I got to do jnp.mean. That will take my vector and condense it down and just give me the average value. Okay. Some people do this with if you should use mean when you can. So here we really want the mean. So that's a little nicer. Okay, let's try it out and see if it works. I'll run it and then I'll see. Okay. And what it's telling us, we ran it. It took 0 seconds. And we got the mean squared error on our 10,000 size training set was 335. Sometimes you want to do the root mean squared error. We can print that out as well by taking the square root. Let's do so we can see how far are we off. Typically, the square root of all this. And there we go. Hopefully this works. Okay, so the square root is 18. We're trying to estimate numbers from 0 to 9, and we're off by 18 typically. So we're doing pretty bad, but things seem to be working. Questions or comments about how we got this? All right, and here's the beautiful thing about this stuff. Once you have defined the function and the mean squared error, the training is always sort of the same. So no matter what function you put in for the mean squared error, no matter what craziness happens inside your function over here, the magic of JAX will automatically figure out how to train it, how to find good parameters. And here's the training loop. And I left out the one important thing, which is the gradient descent. So I'll show you how this works. So the training loop works like this. Global parameters means please use the global variable parameters. If you're doing like actual code and you want to like be smart about things, you don't do this global stuff. But just for simplicity, I'm using a global variable. Then I'm saving the results as I go so I can print out a nice graph. Then I have this for loop. Remember I said avoid for loops if you can. This for loop is unavoidable. This for loop is how many times did we do training steps. And you cannot do the 5th training step until you're done the 4th training step. So this for loop is unavoidable. The for loops are called epochs or epochs. An epoch is using all of your training data one time. So every time we loop through this, we're going to go through our entire batch of 10,000 images one time and update our parameters. Okay, and this start time is going to tell me how long it took to do it. This code over here, it turns out you cannot train 10,000 images at once. 10,000 is too many. So we have a method that splits the 10,000 images into these small things called mini batches, and the mini batches are what is used to train. And so we're going over all the mini batches, and then when we're done, then we've gone all through all the parameters, and we do it one more time. Okay, but here's where the magic happens. I have to put in the gradient. And you remember some classes ago, I spent a lot of time on pen and paper figuring out the gradient by hand. But the magic thing about JAX is it will do the gradient for you. You have to use the command jax.grad. So if you do jax.grad, that will compute the gradient of whatever you put in here. And in our situation, it is the function batched lin_r. So whatever function you want the gradient of, it will do it. Let me make sure I did this correctly and I didn't forget something. Okay, so, oh, okay, yeah, I did the wrong thing. Yeah, okay, this is fantastic. I made a very silly mistake. Let me see what I'm forgetting. Okay, yeah. So this is the gradient of the linear regression function. Is that what I want? No, not the. Well, you got to put in the parameters. Okay, this is true. You have to enter the parameters. So I shouldn't put in the parameters, and then params x y. So that's true. I got to put that in. But this is the gradient of the function. Is the function the thing we're trying to minimize? We're trying to minimize the value of the output of the function. We're trying to minimize this guy, right? This is the output. So this is the function that gives you the output. We're trying to make this as small as we can. We want the output to be small, right? Wrong? Yeah, that's right. We don't want the output to be small. We want the error to be small, right? If the true answer is 4, we don't want to make this negative 100. We want to make it 4. We want to minimize the difference between the output and the true thing. That was what was in our loss function. So the thing you got to do here is not the gradient of the function, the gradient of the loss function. And in fact, we already did, that's why we did the loss function, right? Here I told the computer, this is the loss function I'm doing. This is the thing you minimize. Don't minimize lin_r, minimize the mean squared error of lin_r. And so you would put in the loss function. So here it's called loss func. I made it an input into the thing. So you tell me the loss func, and I will minimize the loss func. Okay, and so this is the right thing. So this does the gradient of the loss function, and then it feeds in the parameters, the x and the y. Those are the x and the y. Those are the training examples. And then it finds the gradients. So that tells you the gradients. And so maybe I'll give you a quick little reminder. We did this some number of weeks ago. When you're doing gradient descent, it is like you are on some surface over here. This x-axis is the parameters, the params. Of course, in real life, it's multidimensional, not one-dimensional. But I got a one-dimensional thing on my picture. And the height of this function is the mean squared error. And we are sitting here, and we have calculated the direction of the gradient, And here is us sitting at params. We want to update the parameters. We want to move in the direction of the gradient. So we want to move in the direction of the gradient. Okay, so here is the right thing. So here's the formula, and it says, please fill them in. Fill in the formula to update the weights and the biases. So I'm going to fill them in. So the formula is W update formula. Take W and add on dW. Take B and add on dB. And that is going to take the weights and the biases from before, the dW and the dB, those are the gradients that I had, and I'm adding to move in the direction of the gradient. Does that make sense to everyone? Okay. So that's how you do it. Okay. This is saying if you're doing accuracy, but all this stuff is just like bookkeeping. Like let's keep track of the score, and then so we can print it out. But okay, here it's going to work. So I'm going to run it, and it's going to tell us what's going on. So remember, our training loss started out as 335. That was the mean squared error. And this will run it and tell us what is our training loss after every epoch. Okay, here we go. Let's run it and hope that it works. And if you use this function called TQDM, you get these cute little slider bars for free, which is really, really fun. So this is telling us 469 is the number of mini batches. So our 10,000 images got split up into 469 groups. And we're working through all the groups. And we're doing this gradient and updating the weights as we go. We're 85% done. The first epoch, almost done. And uh-oh. Man, what does man mean? That means not a number. Your training loss is so big, it has exploded. And that's because there's a mistake in the update rule. So the gradients got calculated correctly. When I did this formula for the update, I did some silly stuff. There's some silly mistakes here. So I guess this is like seeing, do you remember what we were doing with this gradient descent thing? But if you look at this, you should know there's a mistake. Yeah. Minus. This is not gradient descent. This is gradient ascent, right? So I told the computer go up the hill, make the errors as big as possible. That's not what you want. So minus. That's the big mistake that everybody makes. It's very, very important when you make your AI that is like superhuman. You tell it to minimize human suffering, not maximize human suffering, right? Like you get the wrong output and it's a bad day. So that's important. There's one other thing here. When we did gradient descent that I talked about a little bit, something has to go in front of the DW and the DB. Does anyone remember that? Yeah, the learning rate. That's right. So if you go like this, your step sizes might be too big. So in the picture, so first of all, in the picture, I sort of lied to you. The gradient is actually the other way. The gradient is this way. The gradient is always is the direction of largest increase. This is minus the gradient. And you don't want to always step just by minus the gradient, because the gradient might be a vector that's too big. So for example, in this situation, if the gradient is this huge vector like this, then we'll take a step and we'll end up over here. And we haven't actually gone to the valley down here. So you have to scale it by some amount to make lots of teeny tiny steps rather than one too big step. And that amount is called the learning rate. And I believe that is an input in my function over here. Step size. I called it step size. Okay. Step size. And step size is just a number, so this is the right formula now. So I fixed the step size and the thing. Let me make sure that this is right. Okay. And it turns out for this thing, you need a really small step size or it's going to explode. So when you get not a numbers, when you get the nans, often the step size is too big and you're blowing up the computer's numbers. You can fix it by making a really small step size. Okay, I wrote in the small step size over here. Okay, great. So let's try it again and see if it works this time. Oh, I gotta rerun this thing. So I changed the formula, but I have to rerun it to tell the computer this is the new formula. Okay, let's rerun it. Okay, while it's running, great time for questions. Yeah?
Is the step size arbitrary or you're using it proportional to the slope?
Oh, okay, this is a great point. Let me go to this thing. So the dW and the dB are already proportional to the slope. They're the gradient. So if the gradient is very big as the length of a vector, that means the slope is very slopey. So this is like how much we are scaling the vector. And this is like one of the hardest things in machine learning is getting this stuff right. And people have all sorts of fancy methods to do it. But yeah, you don't want this to be too big or it's going to explode, and just scaling it by a constant is like the simplest thing that will work as long as the constant is the right size.
So you pick any number then?
Yeah, right. And again, this is the simplest possible thing. There's all sorts of black magic voodoo on you start the step size high, then you make it low, then you make it medium size, and then you do all this you use a fancy formula. There's all sorts of ways you can make this better. This is the simplest possible way, just multiply by 0.01 or whatever. Yeah, great question. Yeah. Okay.
How did you decide what the step size is?
I ran it, it didn't work, and then I ran it again, and then I kept doing it until it worked. Yeah. So in real life, there's smarter ways to do it, but this is the simplest way, and very often you're doing this. We've done this before. This step size is a hyperparameter. right? So there's the parameters of the network, and then everything else is a hyperparameter. Step size is one of the most important hyperparameters when you do this machine learning stuff. That doesn't exist in like the scikit-learn version, right? So this is one of the hard parts of machine learning, is getting these extra hyperparameters right. And part of the problem is if you get them wrong, nothing works. Like it's not that you get like a slightly worse answer, you just get total garbage. So you got to get it right, and in this situation, it works. I will give you one tip. You can, if you make your step size too small, it will work just slowly. So if you make it too big, it explodes. If you make it too small, it's like takes a long time. So it's an asymmetric thing. You can always try smaller ones. Okay, let's try our thing and see if it works. Okay, so remember, the loss started out at 300 after one step, and then we got it down to 150. That's very good. And I've done the training loss and the test loss, 153 and 150. That means we're probably not overfitting. Like it's doing pretty well. It's generalizing from the test set to the train set quite well. This is one of the great things about neural networks is they generalize well, pretty well. Okay, here's another one. We went down from 150 to 109. Okay, great. So very good. Okay, let's keep doing it. And okay, so here I said make the parameters random and then do this. But now if I just comment out the line where I say make the parameters random, then it'll keep training. So if it doesn't reset the parameters, it'll just use the parameters as before. So now it's like I can add more training steps. Let's do 2 more. Okay. Yeah.
I like every value I am getting different than this. So is it because of random?
Because of random. So remember, when in the initialized network parameters, the key was what time it was when you ran it. So unless you press the button at exactly the same time, then and your clock is on your computer is exactly the same as mine, then you're going to get different answers. Yeah, that's great. Okay, so here it's going down 89, 72. The root mean squared error. Now you can start to do the squared in your head. The root mean squared error is like 9, and here the root mean squared error is like 8.5 or something. So we're getting closer, right? Started out really bad, and it's getting better and better. Let's see what it looks like. So here I'm going to plot some examples. So I took some examples, and here is the picture, and here's what we think it is. So this obviously looks like a 0. Our model thinks it's a -8. Not great. This one is a 4. This one thinks it's a 29. Also not great. This is a 1. This thinks it's a -5. Oh, ooh. 9, it thinks it's 16. Okay, so first obvious thing is our model is linear regression, and there's no reason for linear regression to stay between 0 and 9. And in fact, look, it's doing negative numbers, it's doing 29. Like, wouldn't it be nice if we could just tell the model, please always output something between 0 and 9? And if you're doing the normal scikit-learn stuff, there's no easy way to do that. You can't like do that. Like, you can do linear regression or you can do something else, but there's no like, take this out of your pocket, slap it onto linear regression and call it a day. But with machine learning, there is. So here's what I'm going to do. We're going to take our picture and just update it. We're going to add on one little thing over here. So instead of this being the output, we're going to add on a function. So in the pictures, people sometimes draw these like this. Let me get rid of this thing. They say add a non-linearity. Maybe they draw like a little thing like this. This is a non-linearity. And then what it's going to do is the output will not be this whole thing. The output will be some function applied to this whole thing. So I can take the output, which is between -infinity and infinity, I'll just slap on a new function, and that function will compress it down to be between 0 and 9, and everything will work. So I just have to, in my output function, I just like throw this in, and everything will work exactly the same. You don't have to change anything. And I think this is the first example of like the magic of neural networks. Everything we've done up until now, you're like, dude, why are you torturing me with this? We did it in scikit-learn in 1 second. But now you can kind of see why it's worth doing, is it's very easy to modify. And we can slap on a nonlinearity in like very quickly. So that's the next thing I'm going to do here. I'm going to slap it on. So nonlinear, but still regression. So everything's the same. I'm going to use the sigmoid function to do this. So the sigmoid function, let me make sure, I think it's jnp.exp. Okay, yeah. jnp.exp of x divided by 1 plus jnp.exp of x. That's the sigmoid function, and it crunches -infinity to infinity to 0 to 9. The sigmoid only does it from 0 to 1. Let me do it this way. I'm gonna correct this code here. So the sigmoid is always between 0 and 1. And then in my code, when I do this, the output between 0 and 9, before we did jnp dot of w comma x plus B. And now I'm going to apply the sigmoid function. So I'm going to do a sigmoid of that. Sigmoid of this. That will be a number between 0 and 1. I want a number between 0 and 9. So why don't I just multiply by 9? 9 times that. And now it's all legit. So this will be an output between 0 and 9. Sigmoid is between 0 and 1. 9 times it is between 0 and 9. And I think I want to make sure, yeah, I got to put in a 0 somewhere. Where is the 0? So just like before, I don't want this. I want the 0th entry of this. OK. So now this will work, hopefully. OK. And to check it, I ran it on an example. So here it is running on some examples. 8.9989, 8.9989, 6.82. These numbers are all between 0 and 9. One thing that's a little annoying is they seem very close to 9. Let me just run it and see if it works. OK. Wait, OK, before I run it, questions, comments? Actually, why don't I run it? And you can ask me questions while it's running. So I just slapped on that function, yeah.
So can you go upside?
Yes, yes,
Just want to see.
yes. And there is also a file with the answers you can see at the end of the class. Where do you want to see? You want to see?
Sigmoid function.
Yes, sigmoid function.
Okay.
So it's e to the x divided by 1 plus e to the x. That's the sigmoid function we saw. And then I multiply it by 9. OK. Let's see if it's working. OK, this is great. So the mean squared error with random parameters was 26. After one step, it's 12. After 2 steps, it's 10. So it seems to be shrinking. We can keep going. So let me say, please don't initialize, and let me just keep going. And let's make it even better. Sometimes it helps to change the step size as you go. Like you can sort of like, as a human, make sure it's like working. But it seems to be working fine. OK. 10. OK, what is it? What's the square root of 10 these days? 3. So we're off by like 3 now, right? Typically, we're away from the real answer by 3. Is it going down? Ooh, so it's going down a little bit, but it's a little bit stuck. Let me try boosting the step size a little bit. Hopefully this doesn't explode it. So I kind of get the feeling it's not learning a lot because we're sort of like on a flat region. I want to speed things up a bit. I tried multiplying the step size by 10. There's a chance it'll explode and go horribly wrong.
It's going faster.
Oh no, it was like 10 and now it's 28. So I made it too big and I've gone the other way. Let's see what it does. Yeah, OK, gotta go back. Sometimes you can save your weights and then you can undo. OK, well, I put the 0 back. Clearly, whoever wrote in all those zeros knew what they were doing. But it's worth a try. So yeah, this is like part of the experience when you do these machine learning methods from scratch. Is you'll get some weird stuff like this.
So what if we do 0.00005?
Yeah, that's a good try. Yeah, I should have left it when it was 10. Now I feel bad. Oh no. OK, let's try again. Did I forget to put the 0? OK, I'm going to copy and paste whatever I have written here in the answers. And maybe it's the same. But let's try again. OK, we're in some weird. OK, hopefully it'll work now. Yeah, you have to be careful with this because the sigmoid function has these flat regions. So if the values are very large, you're in these like flat regions where the sigmoid is almost flat. Remember, the sigmoid was this function. And if you're over here, the gradients are very flat, and it's like hard to train. So I might have screwed up the model. Maybe we want to restart.
Now it is getting same.
OK, let me try restarting. We're gonna re-randomize the parameters and try again. Should have quit at 10. 10 was great. OK, any other questions, comments while we're waiting? Yeah.
So we have to classify between 0 to 9 numbers.
That's right.
So we don't have to use the softmax function because sigmoid is used for binary classification.
This is a great point, is that, wait a second, hold on, the original premise here is ridiculous. I'm making a network that has one output. This is like a regression problem. But the problem we're doing is not a regression problem. It's a classification problem. So actually, this whole thing is silly. And the next thing we're going to do is we're going to upgrade it to a classification. But how do you make a classification? You just add more outputs. So instead of having just one output, you're going to have 10 outputs. If you know how to make one output, making 10 outputs is easy. And that's the next thing we're going to do. So assuming this thing works vaguely, all right, I'm going to stop at 19. Not press our luck. Here is what it looks like. 10 was great. We should have stopped at 10. Okay, so this is a 0. The computer thinks it's 1 times 10 to the minus 10. Hey, that's pretty good. This is a 4, obviously. What does the computer think this is? 9. Not great. Not great. Oh, this 1, it thinks it's a 6 times 10 to the minus 12. This 9, it thinks it's a 9. So I think what it's doing is it's always outputting either, it's too far into the weeds on one side or the other side. It's always outputting like really small numbers or really big numbers that saturate at 0 and 9. So what I have to do in this situation, let me try to fix. Yeah, okay, one thing you can do is start it closer to 0. So why don't I think in the initialized network parameters, let me get the initialized network parameters and start it closer to 0. And I think there's a scale function. Okay, let me do this. Comma, scale equals, and I'm going to try 0. That's the default. Let's try making it 100 times smaller. So what this is going to say is start the parameters close to 0. When you start the parameters close to 0, that's saying start close to the middle of the sigmoid. So if the parameters are too big to start with, you kind of get stuck in these regions, and it doesn't work as well. So let's see if that improves it. Ah, okay. So by starting close to 0, we improve the model quite a lot. Hopefully this one's not huge. It is actually still improving, because it could be now that the learning rate is too big. But okay, well, I'll take it. 3.3. Okay, so the mean squared error now is like 2. Let's see if it improved. Okay, so this one, 0, it thinks it's a 2. This one, hey, look at this. 4.1. Hey. All right. That was very good. This one, it thinks it's a 1. It thinks it's 1.9. And this 9, it thinks it's a 7.6. Okay. So it's working pretty well. I think you got a sense of how the important steps in the machine learning thing. And actually, this whole thing is ridiculous. I showed you how to do a regression model. So this model outputs a number, but it is a classification problem. So of course, you shouldn't do this, but actually, this is the first step in doing what we're going to do next, which is let's just copy this a bunch of times. Okay. So instead of taking this model, the new model we're going to do is like this. We're going to have the input over here, the input, and then we're going to have this. I'm going to call this the logits layer, like here. And there's going to be 10 of them. This one, there's 10. There's 0 to 9. 10 outputs. And these are the logits. This is going to be exactly the same thing. It is matrix multiplication. And I'm just going to do exactly what I did before. I'm doing it 10 times, right? So what I did before was to get one of these, got to do 10 of them. And in fact, it's very simple to do. In the code we wrote, it's like 1 character to get this. Let me show you what it is in this thing. Okay, so this is our next topic. In fact, what we're doing is logistic regression. The output, instead of being a number, the output is now a vector. It is size 10. So the output, I think, should be 10. There's 10 digits. Let me make sure that this is correct. I'm not missing something. Okay. Logistic regression. Okay. Layer sizes. Okay. 10. Okay, actually, I think I just want this to be 10. 10. And that's because output size gets fed into layer size. So the layer sizes are now 784, 10. That is the little picture that I drew. And there we go. I got the sigmoid function. I got the x and the WB. What are the logits before it was the dot product? It's still the dot product, I'm pretty sure. Yeah. So it's JNP dot WX plus B. And this time, there really is no 0 after that, right? Because now it's a vector. So this dot product of W and X, W is an array now, and this is really doing the matrix multiplication of WX, and B is a vector of size 10. And that's because there's a B for every single guy. So this guy over here is a vector of size 10. So W is a matrix, and in fact, it's size 10, 784. And so when you multiply by the vector x, which is a vector of size 784, when you do W times x as matrix multiplication, you get a vector of size 10, and the biases are size 10. So this is the right way to get the logits. Okay, there's no 0. Questions about that? So I'm upgrading the thing to work with logistic regression, and so far I've put in the formula for what the logits are. It's actually identical to what we did before, which is why we did what we did before first, so we would understand this one a little bit better. There's the next thing you got to do is you got to convert from logits to probabilities, right? So there's a nonlinear function to convert from logits to probabilities. Probabilities. And I believe we did this one as well earlier in the course, probabilities. How do you convert from logits to probabilities? There's some nonlinear function that eats all these things and outputs all these things. And that function is the multivariable version of the sigmoid function. It's called the softmax function. And we did it in class. What it is you do e to the xi divided by the sum of e to the x, let's call it j from 1 to n. So what you do is you take the exponential of every single one of these, and then you divide by the sum of the exponentials. Okay, and there is an easy way to do that. We can do it by hand. Again, you can do all these things like automatically, but I think it's nice to do it over here. So this gives the log probabilities, and the function is, I just do jnp.exp of the logits, and then I do divided by the sum of the logits. Of the logits again, and I got to divide by the sum. So this is the softmax function, if I got the brackets right, which I did not. Okay. Okay, you got to be careful here. When you do sum, we want to sum along the 10 dimension, not the dimension of the batch. So do I need to be careful here for this?
So wouldn't have been this max 0?
Oh, okay, I'll explain that in a second. Don't worry about that. Worry about this formula. I'll explain that in a sec. So this is doing that e to the thing. Those are the logits. Log sum x, log p. I just want to think for a second before I say something that is totally wrong, and then I'll have to backtrack, and it'll confuse everyone more. Okay, this is correct. Okay, okay, I understand why I'm confused. This is the formula for the probabilities. Okay, this is good. This is the probabilities. This is the probabs. Okay, this is the formula for the probabilities. That's exactly what we want. Questions or comments about this? It's all correct. As written, I wrote the right formula for the probabilities. We've done this earlier in the course. Tell me how rusty it is. If I should explain more, or if you vaguely remember, then it's okay. Okay, here's the thing. It turns out, in the next part of the function, we don't actually need the probabilities. We need the log of the probabilities. So we're not actually going to use the probabilities directly. We're going to calculate their log. So you could just do, at this point in time, you could do the log p equals the log of the probabilities and be done. But now you've done an exponential and then you did a log. You're just undoing work for yourself. So why not? Let's just do it directly. What is the log of this thing? Well, the log of the x is the log. So that's the logits, right? So instead of doing the exponential and then taking the log, just do the thing originally. And then when you do the dividing, that's a minus sign in log space. And then you're doing the log of the sum. So that's exactly the formula that Google is suggesting for me. So I can skip the step of doing the probabilities directly and go straight to the log of the probabilities. So that's the formula. Okay. Let me write it down on the blackboard as well. So this formula, these are the probabilities. These are the probabs, are this. What are the log of the probabs? The log of the probabs. So you have to do the log of this formula. Well, you're going to get xi minus the log of the sum of e to the xj. J equals 1 to n. So in other words, the e to the x, when you do the log, gets undone. The division becomes a minus sign, and then the sum is inside the log. That's all I do. Questions or comments about that? Okay. So this is perfectly correct. This is perfectly mathematically correct. There is one super annoying thing that will make your computer crash if you do this. And that is if the logits are very close to, what is it? If the logits are very large, when you do the exponential of a large number, the computer will explode and just get mad at you. So this won't work if the logits are too big, because the computer will complain and say, hey, I cannot do the exponential of 1,000, man. Like, that's too big of a number. So this line is a problem if the logits are large. So there's one other trick you do, which is I subtract a constant number from the logits. So the logits are never larger than 0. That's logits max 0. If you add a constant to all of the logits, it does not change the log p's. So by adding any number you want to the logits, it will not change this line, but it will stop the computer from complaining. So instead of doing logits directly, I'm going to do logits max 0. Very small technical reason that just makes the computer complain less often. Okay, so that is the model. That is the logistic regression log p. And so what we have done so far is we have in the computer told the computer how to do this model, where we first do one layer of linear stuff, then we do a softmax function to get the from the logits to the log probabilities. That's what we've done so far. Questions or comments about that? The next thing we have to do, remember before, we did two things. We first told the computer, here is the model we're using, and then we said, here is the error function we're using, right? So before, we said, this is the training loop. Yeah, here are the things, right? So first we did the model, and then we did this mean squared error loss. But when you're doing a classification problem, you don't use the mean squared error loss. Use a different loss function, okay? So that's the next thing we're going to do. We're going to type in, tell the computer, this is how you calculate the error, okay? We're going to implement the cross entropy loss. And all of that will happen next class. So next class, we're going to keep going with this. We've finished doing the function. We got to put in what is the mean squared error loss, and then we're going to do logistic regression on this. And then you're going to see that once you know how to do logistic regression on this problem, making a, quote, neural network is very simple. There's like a couple of things you've got to add. So another way to say it is, seems like we're doing just logistic regression, but we're actually learning how to combine these Lego blocks together to make really complicated functions. And if you know how to do this one, and you know how to do this one, you can combine them, you can do anything. That's what we'll do next class. Okay, so I'll stop there, and we'll see you guys on Wednesday, where we'll do more of this stuff. Don't forget to do your